Part 3 of this video series ended up getting a little on the long side, so I'm going to be splitting it up into two videos. In Part 3a, we're going to focus on the slope of regression lines. Now, why is the slope so important? Well, if we look back at our example from the Minneapolis pub of hot wings versus beer, right, that slope of this line, which certainly looks positive in this picture, tells us that as hot wings consumption goes up, beer also tends to go up. So, really, when we're testing for a relationship between beer and hot wings in this scenario, right, is there a significant relationship between hot wings versus beer? What we're really trying to do is test a null hypothesis that the slope of this regression line is 0 versus an alternative that it's not equal to 0. Right? So under the null hypothesis, we're assuming that they're independent, there's no relationship, and we're trying to provide evidence against that status quo. The second class of questions we're going to be addressing in this video deals with confidence intervals, and we'll mainly get into, in the second part of this video, the relationship between confidence intervals and what we call prediction intervals. So as a practical application of where you might see these quantities arise, let's suppose the pub sells a 12-pack of wings and they would like to know how much beer they should expect to sell. Well, we can already give them a number value, right? We could just look at our predictions here based on our line and say, well, it looks like they'll sell about 26 ounces of beer for every 12 pack. But what we'd really like to know is, what can we say about the range of plausible values? And that will take us into this idea of confidence intervals versus prediction intervals in part 3b of this video series. So to begin, we're going to need to go back, take a step back towards what we did earlier in the class and discuss the difference between estimates and estimators. So estimates, MLEs, as we first compute them, are numbers, right? We throw in some data and we get out this number, which is a point estimate for some unknown parameter. However, if we want to do things like derive confidence intervals for estimates, for unknown parameters, or do inference about unknown parameters, then we need to switch our point of view and consider these MLEs as estimators, right? Random variables themselves. Because once we consider them as random variables, we can talk about things like what is their expected value and what is their mean. And as an example of that, when we were talking about the MLEs for mu and sigma from a normal random variable, we knew that the MLE for sigma was the sample mean, y bar. And if we consider it as an estimator, then we're looking at statistical properties of the random variable, which is the sample mean of our individual observations, okay? And we know some things about this. For example, we know that its expected value is mu, right? And that brings us to our second point here, which I wanted to recall, which is that an estimator is unbiased if an estimator, theta hat, is unbiased for theta if its expected value is indeed what you're trying to estimate, right? So if on average it gives you the right answer. So based on what I just said above, we conclude that y bar is unbiased for mu. It's an unbiased estimator of mu. Right? Whereas the sample standard deviation, okay, which was let's talk about variance instead. So the sample variance, which was 1 over n times the sum of the yi's minus y bar squared, we saw in the last video series that this is actually biased, right? But that we can unbias it if we divide by n minus 1 instead. Okay. That's going to be important as we move forward. The third point I wanted to remember about estimators is that the variance of an estimator measures its efficiency relative to other estimators, right? So the variance is a measure of how precise your estimator is at estimating what you want, and it's really that variance which helps us form confidence intervals and do hypothesis tests and leads to the idea of standard errors and whatnot for the quantities we're trying to estimate. So if you're following, hopefully so far, let's look at the slope from our regression line as an estimator. So first of all, recall that yi in our simple linear model is beta naught plus beta 1 xi plus epsilon I, where these error terms, the epsilon i's, are normal with mean 0 and standard deviation sigma. Also recall that we had a formula beta 1 hat for the slope in this simple linear model, right, that we derived in the last video. So the first thing we're going to do is we want to think of this slope as an estimator. So we're going to place the little yi's with big yi's. And if we do that, we get an expression as follows. Sum of the yi's, and the denominator will stay as it was before. And sum of the xi's squared minus the sum of the xi squared. Now, the trick to discussing this is to simplify this expression so that we only have some constants times the yi's. Okay, and we'll see why that's so important. But let's do a little algebraic manipulation here. Let's do some algebra shit and get this in a form that's a little bit easier to work with. So notice in the numerator, if you factor out n, in fact, if you factor out n from both the numerator and the denominator, okay, then the n's will cancel. And in the numerator, what I get? Sum of xi, yi. So if I factor out n, the sum in the second term actually turns into the sample mean. And when I factor out n in the denominator, we end up with xi squared minus 1 over n sum of the quantity squared. And if we simplify the numerator, if we factor out the yi from both sums, we end up with the following. So we have sum, the sum should be out front here. This video is just going to go because, hey, that's what's happening today, right? So the yi is a part of the sum. So let me rewrite this as xi minus x bar, and then yi. And then in the denominator here, I'm going to have this expression, which I'd like you to take a minute and show can actually be rewritten in a much simpler form as the sum of the xi minus x bar squareds. Okay, take a moment to do that. It's just a little bit of algebra, good for your bones at this point, and good for your, I shouldn't say bones, good for your neurons, I guess, your math neurons here. Okay, now the point here is that once we've made all these simplifications, this quantity in front of the yi's is just some constant here. Summarizing the calculation on the previous slide, we've managed to write beta 1 hat as a linear combination of the yi's. What does this gain us? Well, recall that based on the simple linear model, excuse that slide switch there, the yi's themselves are normal random variables. They have a mean, which is beta 1 plus beta naught plus beta 1 xi, and they have a standard deviation sigma. So by writing beta 1 hat as a linear combination of known random variables, which are also independent, we can compute its expected value and variance directly. Now, to make this calculation a little simpler so you can see where it's going, I also want to remind you of a fact that occurred on the previous slide. So take a moment to convince yourself of this if it doesn't make sense, which is that that denominator down there can be rewritten as the sum of the xi squareds minus x bar times the sum of the xi with a little bit of algebraic manipulation. So we're going to see that fact come into play. Okay, so are you ready? Before we start, think about what you want the answer to be. When we take the expected value of beta 1 hat, of course things don't always turn out like we want to in math or the real world, but we can always hope, right? If we take that expected value, what I'd like to get is beta 1, right? Because I want it to be an unbiased estimator. So let's see what happens. Well, expected value is a linear operator, so I can distribute the expected value into the sum. Now the yi's all have a known expected value, which I can substitute in here as beta naught plus beta 1 xi. And then I can distribute the sum and factor out the beta naughts to get beta naught times the sum of the ai's plus beta 1 times the sum of ai times xi. So let's take a look at each of these remaining terms here. First of all, the sum of the ai's. What's going to happen when I do that? Well, the denominator here, notice, is just a constant, which let's denote that by s sub x just for the slide. It's a sum whose value depends on x. Okay? But notice that, so when I take the sum of the ai's, I'm going to get some constant here, times a sum of the xi's minus x bars. Now, whenever you see this sum, you know it's going to be 0. Okay, there's a couple reasons. One, you could just algebraically manipulate it and distribute the sum, but also the mean of a bunch of numbers is their balancing point, right? So this is sort of the center of mass of these observations, and hence it's the point for which the sum is 0, really. Okay, so that kills off this first term. Yay, we're good to go so far. How about that second one? Well, what I need to do, or what I'd ideally like to do, is show that this sum is equal to 1, right? And then I would only be left with beta 1 in this expression. So, is it? Let's check. If I multiply the ai's times the xi's and factor out that s sub x term, I would get the sum of the xi squareds minus xi times x bar. And so notice that is 1 over sx times sum of xi squared minus x bar times the sum of the xi. And now if you look at the fact I recalled from the previous slide, sure enough, those two cancel out and we just get 1. So yay, it's unbiased. Let me switch colors so we can put it in here. So it's an unbiased estimator. Its expected value is what you're trying to estimate. Now, what about its variance? So its variance is important for forming confidence intervals and other things. Okay. So the variance of beta 1 hat. Well, using properties of variance and the fact that the yi's are independent, we can write this as a sum of ai squared times the variance of the yi's. Right? And the variances of the yi's are all sigma squared. So this just becomes sigma squared times the sum of the ai squareds. And when I add up the ai squareds, I'm going to factor out that s sub x factor again. Notice I'm going to get s sub x squared because I'm squaring the terms, but then this other term here that I'm summing is also s sub x. So I end up just getting sigma squared over that sum from the denominators of the coefficients a sub I. Right? So now armed with these two facts, the variance of beta 1 hat and the mean of beta 1 hat, we can get back to our hypothesis testing question, right? If we want to compute the test statistic for a hypothesis test where the null is the slope is 0 and the alternative is the slope is non-zero, then the test statistic we can form is just beta 1 hat minus its mean under the null hypothesis, which is going to be 0 in this scenario, divided by its standard deviation. I'm just going to use that s sub x term again here to denote that pesky term that we have to keep writing otherwise. So great. So then basically to perform this hypothesis test, you'd find the critical z scores, find z critical, right, or z star as we sometimes write it, which gives us the appropriate area to its right under the curve, and all is good, right? Well, you can probably see the problem here, which is, what the hell is sigma? Sigma is this variance about the regression line, which is unknown. Okay? And in fact, if you recall from the last video, this same problem was what set us off on that weird path that took us through the chi-squared and the t-distributions. And that situation arose in what we called a one-sample t-test, where our null hypothesis was that the mean is equal to some specified value mu naught. The test statistic in that scenario was also standard normal under the assumption that sigma was known, but if sigma wasn't known, what we had to do was replace it with the sample standard deviation, and the resulting statistic we showed had a t-distribution with n-1 degrees of freedom. So you can guess that there's going to be something similar happen here. We want to be able to say, well, I don't know sigma, so I'm going to replace it with something, and then the resulting distributions are going to flip from being a z distribution to some kind of t distribution with an unknown degrees of freedom. So coming back to our scenario, here was that test statistic z from before. So I want to replace this one with beta 1 hat over s, and then there's that s sub x term here. But the question is, what should I use for this s, right? What is that s going to be? Well, you'll probably recall that the MLE for sigma, the MLE for sigma squared was 1 over n times the sum of the yi, I'm going to write it as an estimator, minus the yi hat squared. So it seems natural to use something related to this quantity. However, in order to get a t distribution out of things, right, we need to have a quantity down here which is related to a chi-squared distribution. And although I am not going to show you the details of this here, they are written out in the appendix from chapter 11 in our textbook. But it turns out that this quantity, okay, is indeed a chi-squared, but now with n minus 2 degrees of freedom. It might seem kind of arbitrary to put this minus 2 in here, but it's really not arbitrary at all, and it actually follows the rules of how our degrees of freedom have been working. In the chi-squared video, we noted that you sort of lose a degree of freedom for each parameter you have to estimate. Well, when we're computing y1 I hat, we had to estimate 2 parameters, which were beta naught and beta 1. So it only makes sense here that we lose 2 degrees of freedom in this chi-squared. In contrast, if you don't mind me flipping back a moment, right? When we, it was this one. When we go and we estimate mu by x bar in this scenario, we only estimated 1 parameter, and so we only lost 1 degrees of freedom. So working off this idea, what we're going to do in order to get an unbiased estimator of the variance, we're going to define S, and this is often called the standard error of the residuals, or SER in some situations. Okay? We're going to define this as the square root of 1 over n minus 2 times the squared deviations of the observations from their predicted values. Right? And this is called the standard error of the residuals, because these terms in parentheses, you'll recall, are called residuals, differences between actual and expected ones. And it's this SER, the standard error of the residuals, that we are going to use in our statistic here to end up with a t distribution and n minus 2 degrees of freedom. Now I'm going to come back and show how to compute all this in R for our beer and hot wings example, but I wanted to first take a moment to point out the conclusions and also discuss how we can use that same fact to get a confidence interval for beta, which in this slide you can see as elsewhere. I have forgotten my subscripts, so let's just take a moment here and change all these betas to beta 1s because we're dealing with the slope. So the conclusion is that to test for zero slope, our test statistic is going to be beta 1 hat, which we have a nice formula for, divided by S over the square of the sum of the squared deviations of X from their mean, where S is that standard error of the residuals again, right? Standard error of the residuals. And based off that same reasoning and the same t distribution, we can form confidence intervals for beta 1 as our estimate, our point estimate, plus or minus the t critical values. So that's chosen based on the confidence interval percentage, and then times this quantity right here, which this is basically, you could think of this as, it's the standard error of beta 1 hat, right? It's the estimate of beta 1 hat's standard deviation. So let's see how that turns out. To follow along with this R code, please take a moment and download that Beer Wings data, which is posted on Canvas. The first chunk of code here up until this end of this highlighted region is just replicating what we did in the last couple of videos, which is compute the formulas for the coefficients B1 and B naught, or you could think of these as beta naught hat and beta 1 hat, because we showed that the MLEs are the same as the least squares estimates. The second 2 lines here just are plotting the data against those to make sure it's a good fit. And scrolling down, we can see that, yeah, it passes the smell test. It seems to look all right. Now, this next part is the newer code. So SSR, what this is doing is it's computing the sum of the squared residuals, the sum of the y's minus their predicted values, okay, squared. And then the SER, that's the standard error of the residuals, which is just the square root of this quantity divided by n minus 2, the degrees of freedom. Finally, we've got SE of B1, that's the standard error of beta 1, which we derived a formula that said it should be the standard error of the residuals divided by the square root of this complicated sum, well, not really that complicated sum that involves x, the differences between x and their means, the square differences. We compute our t-statistic. It's just beta 1 hat over its standard error. We compute a critical value from the appropriate t distribution, and I'm assuming the typical 0.05 alpha level here for the test, so I would use the 97.5 percentile of the t distribution. And then we look at what our critical score is and what our t-score for our data is, and in this case, the critical t turned out to be pretty close to 2. That's, I guess the sample size is fairly large, so it's not going to be so different from the z-score, which would have been 1.96 in this case. And the t-score for our data turned out to be 6.686, which is definitely a lot higher than the critical cutoff. So we can conclude from this that the slope, right, of that regression line is significantly non-zero, excuse me. So there is a significantly positive relationship between beer consumed and number of wings consumed at this pub. Okay. Now we could add to this a second calculation, which would compute a confidence interval for beta 1. We would just have to do the single line here, which would say beta 1 minus, we would take the t critical and multiply it by the standard error of beta 1. And then we would also do the same thing, but with a plus. And if I run that code again, where did you go, code? We see that this is now a confidence interval for the slope in our line. So in the next video, we're going to take this a little bit of a step further and not just compute the slope or a confidence interval for the slope, but compute a confidence interval for the actual value that you would predict for different possible inputs or different possible wing inputs into our model.